Hello everyone and welcome to the 12th lecture in the course Solar Photovoltaic System Design. So in the previous lecture we looked at the basic concept of a solar cell, what is the structure of a solar cell and some basic understanding of its working. So today we will go much deeper into the working of a solar cell and we will see what exactly is the phenomena happening in the different depths of a solar cell. So right from the top surface to the body of the solar cell and in the very bottom of the solar cell, what are the different phenomena which are happening and how it contributes to the overall working of the solar cell. So to begin with today's discussion, let me just remind you of this structure of the solar cell which we saw in the last class. And as you very well understand now that a solar cell consists of a p-n junction, just like the photodiode, and the entire magic, the so called quote unquote magic of the solar cell happens around the p-n junction. So as we can see in this schematic diagram, there is this p base. So you have the base material of the solar cell, usually we put it p type base material, and the n type semiconductor forms the emitter. So you have the base of p type semiconductor and you have the n type semiconductor as the emitter. Also another important thing to be noticed here, as you can see, is that it says n plus emitter. So there is a plus superscript with n. So what does that indicate? That indicates that your n plus side is very heavily doped. So this is heavily doped. The doping intensity on n side is much higher than as compared to the p side. The typical order of higher doping, if you look at the n plus is to p side doping, it is usually of the order of, let us say, around 100:1, or can be little more or less than that also, but this is like one typical order of magnitude. So that means on your n side the concentration of the dopant is almost 100 times of that of the concentration of the dopant on the p side. So there is this concept, we call this as the asymmetric doping. So the p-n junction for solar cells usually comes with asymmetric doping, higher doping on one side and lower doping on the other side. And as a result of that, what you see in the structure of the solar cell is that your n plus side is a very small magnitude. The depth of the n plus side is much lesser as compared to the depth of the p side. And similarly, if you look at the p-n junction, the junction is formed here between the dotted lines, the dashed lines. So you have p-n junction little bit on the n side and much more on the p side. And the depth of the depletion region or the space charge region, as we call it, that also will be asymmetric. And the depth of space charge region, so if you look at the depth of the space charge region on the n plus side and you compare it with the depth of the space charge region on the p side, it will be in the reverse ratio. So if we are doping in the ratio of 100:1, so your depth of the space charge region on n plus side to p side would be of the order of 1:100. And that is pretty much common sense, you can say, because if you recall one of our earlier discussions in the course, we talked about the formation of a p-n junction, how a p-n junction forms, and you have a p type material and an n type material which you are placing together. There is a heavy concentration difference between the concentration of the charge carriers on the two sides of the boundary of the p and n material. So what will happen is that the excess electrons from the n side will diffuse to the p side, because on the p side you have excess holes, or basically those are the vacancies of electrons, and on the n side you have excess electrons. So these excess electrons from the n side go to the vacancies or the holes on the p side, in such a manner that within the space charge region all the charges are neutralized. So there are no free charge carriers in the space charge region, and as a result of that there is an electric field which emerges here. So because electrons have left the n side, this becomes relatively positively charged, it acts like a positive plate of the battery or a capacitor, and whereas you have excess electrons which have come on the p side, so that acts like the negative plate of the capacitor, and in between there is a sort of dielectric type behavior, not really dielectric but dielectric type I am saying, because there are no excess or free charge carriers. But the interesting thing is this electric field which comes here across the p-n junction. So, the entire working of the solar cell rests on this particular phenomena of the electric field in the space charge region. So, this is little bit of recap of what we did earlier and some more things we have discussed so far. But now let us go ahead and look at the detailed working of the solar cell at different depths of the solar cell. So, to understand that, we will use this particular two-dimensional projection, or the, you can say, the cross-sectional view of the solar cell. So, now you can see here there is some magnitudes of depth also mentioned on the right hand side of this figure. These are just indicative numbers, they are not really like de facto numbers which have to be there, but just to give you a sense. So, if you see here, we are starting with this x axis, or the depth starting from the surface of the solar cell. This is x equal to 0. Then your emitter is a very thin layer. So, the n plus emitter, and the thickness of the emitter will depend upon the extent of doping. Higher the amount of doping, higher the relative concentration of dopant on the n plus side, smaller will be the depth of the n plus emitter. So, like in this example here, you see they have shown this as x equal to 0.1 micrometer only. So, those are the order, so it can be a 0.1 micrometer, can go maximum up to, let us say, 1 micrometer in that particular range. But let us continue with this example with this number only. So, you have x equal to 0.1 micrometer up to the depth, that is the depth up to which you have the n plus emitter. And on the p side, if you see the final extreme end of p base, it says x equal to 180 micrometer. So, here the ratio of doping would be even more stringent. So, if you look at the n plus is to p side, if you look at the depth of the space charge region, let us say d on the n plus side compared to the d on the p side. So, you have 0.1, if you see it is in fact even lesser than 0.1. In this case, I mean, let us say I am taking a typical value here. So, suppose it is 0.05 micrometer here, and here it says x equal to up to 1 micrometer is where the space charge region is. So, if you see, it is almost 1:20 type of scenario. So, depending upon that relative concentration, you can work out the depths, but the idea is that always the heavily doped side, n plus in this case, would be of a much lesser thickness. So, you have some depth up to which you have the emitter, then there is another depth, in this case it shows up to x equal to 1 micrometer till where you have the space charge region. And then you see here, as you can see on the left hand side, the nomenclature is given, you have n plus emitter, space charge region, and then we are considering one diffusion length below the space charge region. Typical values of your diffusion length are of the order of 100 micrometers. Now, this is also important, we will see why it is important, but for now let us understand the nomenclature. So, we are saying the third region, so there are these 4 regions of the solar cell. The first region I am saying is this n plus emitter before the space charge region. Second region I am saying is the space charge region itself. Third region we are saying is up to one diffusion length below the space charge region. So, like almost of the order of 100 micrometer below the space charge region. And then the fourth region we are having is much deeper in the solar cell beyond the one diffusion length boundary. So, after x equal to 100 micrometer till x equal to 180 micrometer, let us say, we saw in the last class typical depth of solar cell is of the order of 200 micrometers or so, can go up to 500 micrometer also, by the way, depending upon the design and some parameters, but this is the typical number like 180 200 micrometers. So, the fourth region is below the x equal to 100 micrometer depth and in the bottom of the solar cell. So, in these 4 regions, the behavior of the photon is different and the effect of the photon absorption is different actually. So, to understand that in depth, we will use these 4 sample photons. Photon 1, which is getting absorbed very early in the solar cell, even before the space charge region in the n plus emitter, that is photon 1. Photon 2, which is penetrating the n plus emitter and going somewhere, getting absorbed in the space charge region. Photon 3, which is penetrating even further and it is getting absorbed between one diffusion length below the space charge region, and photon 4, which is going much more deeper in the solar cell and it is getting absorbed only after one diffusion length below the space charge region. So, each of these photons, in case if the photon energy EPH is more than the band gap energy, we will consider that example where our sample photon which we are considering is having energy more than the band gap. So, each of these photons will produce a electron hole pair, and that is what is shown here in the figure. You can see photon 1 is producing one electron hole pair, photon 2 another one, third another one, and then the fourth photon also producing one electron hole pair. But what will be the fate of these electron hole pairs, how they will behave, whether they will contribute to useful output of the solar cell or not, that will be very different in each region of the solar cell. So, let us look at it one by one. So, to begin with, let us first look at absorption in the emitter. So, we have absorption in the emitter. So, we are considering right now this first photon, and it is getting absorbed, as you can see, very much near the surface of the solar cell above the space charge region in the n plus emitter. Now, what will happen to this electron hole pair? Let me ask you that question. Think about it for a moment, and if you apply whatever concepts we have discussed so far, you can find the answer actually. So, what will happen here basically, this region as we said is the n plus emitter, it is very heavily doped. So, as soon as a photon gets absorbed here, and let us say the photon, always all these photons we are talking about, we are assuming that they have energy more than the band gap. So, it has more than the band gap energy, it will raise the electron from the valence band to conduction band, it will create a electron hole pair. But by the way we have defined this, it is n plus emitter, there is a very high density of your electrons which are present here. Due to this very high density of electrons, even if you create the split between the electron hole pair, even if you separate out the electron and hole, as soon as you create that split, some other electron which was available here, it will come and sit in the position of that hole, it will occupy that hole. So, basically in this region what is happening, let me draw a little more detailed schematic. So, let us say I am calling this as the n plus side. So, as soon as your photon gets absorbed, you create one electron and one hole pair, then there is so many extra electrons which are already there, because this is the n plus emitter, very heavy doping of electrons is there. So, as soon as you create this electron hole pair, suddenly another electron comes and sits in that vacancy, another electron hole pair gets absorbed and you create that split, to indicate the split here. You pull out one electron from its position, you create the electron hole pair, but then again, because there are so many excess electrons already present around this, as soon as it is created, another one comes and sits in the place of the previous electron. So, basically to summarize, what we are saying here is that any electron hole pair created here is lost almost instantaneously, and that is not really desirable. So, this type of recombination which happens, you split the electron and hole pair, you create the electron hole pair by absorbing the photon, but then those excess electrons are so many in number that they come and just occupy the hole or the vacancy. So, the recombination happens quite fast and instantaneously. So, due to this particular phenomena, this particular region above the space charge region, so let me also indicate in my figure here the space charge region, let us say is this one. So, the portion of your emitter above the space charge region, it is not really productive for production of any photocurrent, and that is why this layer is also called as the dead layer. So, that is the dead layer. Obviously, we want the solar cell to produce current, so we won't want much of our solar cell to be dead layer. We would like to have active layers in the solar cell, but the top layer with heavy n plus emitter doping, that intrinsically due to the nature of the phenomena which is happening there, it acts like a dead layer. As soon as you create an electron hole pair, some other electron comes and sits in the place of the hole, and there is a recombination happening. So, it does not contribute any effective output or output current to the external circuit. So, we would like to minimize the dead layer, we do not want the dead layer to be much larger in scope, and that is why now you can appreciate this heavy n plus doping. So, if I make this n plus doping very heavy, then what will happen is that if I just cut a thin slice, so basically with this asymmetric doping, what happens, let me just indicate with another diagram here. So, suppose if I have, let us say I am making a solar cell like that. So, you have p side here and n plus side here, and I have doped the n plus side very heavily. So what will happen is that even a thin slice, if I take a thin slice of material from the n plus side, the number of excess electrons on this side will be sufficient to occupy the number of excess holes which are present in a much larger depth on the p side. And by this phenomena I am ensuring that my n plus emitter need not be much thicker in depth. I can have a very thin layer of n plus emitter, and out of that thin layer also one small even thinner layer will have as much sufficient number of electrons that they can diffuse to the p side and occupy equivalent number of holes. So as I already mentioned, if my doping ratio is 100:1, then my depth ratio would be just the opposite, 1:100. And by this I am ensuring that my dead layer is minimized. I do not want a high depth or larger depth on the n plus side. So that is the dead layer, and any photon which gets absorbed in the dead layer is basically lost. So this is like a lost photon, it does not contribute to any useful photocurrent output or output of the solar cell, and that is why, as we discussed, we want to keep the minimum depth for the dead layer. Then let us go to the second layer. The second layer in the solar cell operation is what we are defining as the space charge region. So this second region, space charge region. Now this is actually the most productive, most fertile portion of the solar cell. And why is that there? Because we already discussed, because of this electric field. So as we discussed about the formation of the space charge region, excess electrons have left the n plus emitter, so this becomes relatively positively charged, and excess holes have been occupied on the p side, excess electrons have come to the p side, so this becomes relatively negatively charged. So these are like the two plates of a battery, let us say. So you have electric field going like that from positive to negative terminal. Now as soon as this, let us say this photon 2 here, which is getting absorbed in the within the space charge region, as soon as this photon gets absorbed, this electron hole pair gets created, and because of this electric field, naturally the electron is absorbed to the positive plate of this electric field, and the hole is absorbed or attracted to the negative plate of the electric field. So that is a natural phenomena, because opposite charges attract. So my electron gets attracted to the positive plate and it goes to the n plus emitter. Now in the n plus emitter, as we already mentioned, there are a lot of excess electrons which are there. So you have a lot of excess electrons which are already there. One more excess electron comes, no problem, it will not recombine, already majority charge carriers are there, electrons, and so it can easily travel through this, it gets collected through the fingers or the current collectors on the top surface and goes to the external circuit. Same way the fate of the hole here, the hole which is getting attracted by this electric field to the p side. Now there are already excess holes, lot of excess holes which are already present here, one more hole has come, no problem, it will not recombine, very less likelihood of recombining, and it can travel and find its way through the p base to the external circuit. So this space charge region is actually the best region with respect to output of the solar cell. So this is the most productive, we can say, or most fertile region, we can say, with respect to generation of photocurrent from the solar cell. So this is highly desirable. Any photon which gets absorbed in this region, space charge region, most likely is that it will contribute to useful photocurrent and produce some useful output of the solar cell. So this is actually the most desirable region. Then we go to the third region, up to 1 diffusion length below the space charge region. So this is my third region here in the solar cell. As we said, this is 1 diffusion length, which is almost of the order of 100 micrometer for typical doping concentrations in the solar cells. Again, diffusion length, as we talked about it in the earlier class, depending upon what is the doping density and what type of material we are using, the diffusion lengths will be different, but this is just the typical number of the order of 100 micrometer. Now what happens here, you see, so we are considering the fate of the photon 3. Photon 3 is getting absorbed somewhere in this third region up to 1 diffusion length below the space charge region. Again, for all the other photons, we have assumed that the energy of this photon EPH is greater than energy of the band gap EG. So, it is also producing electron hole pair. Now, what will happen here is that when this electron hole pair gets created, this electron will sort of wander aimlessly here and there, because there is no driving electric field to suck it up. It will sort of wander here and there aimlessly. But then there are two things. One thing is that the p side does not have a very high concentration of dopant. So, it is not very likely that immediately some hole will come and recombine with the electron due to the lower doping concentration on the p side. That is the first thing. Second thing is that we are still between one diffusion length below the space charge region. So, what it means is that there is a very high likelihood that while this electron is sort of wandering aimlessly, it might land up near the edge of the space charge region, because it is within one diffusion length. So, there is high probability that before getting absorbed, it can land up at the edge of the space charge region. And suppose by chance this electron lands up near the space charge region, the outer boundary of the space charge region, then the electric field which is already present in the space charge region, that becomes active to pull up the electron and send it to the n plus side. And once it is sucked up to the n plus side, then again it will find its way to the current collector on the top side and contribute to photocurrent in the external circuit. So, this third region also is this is also quite productive, we can say. It is not as productive as the space charge region, but overall quite productive with respect to the photocurrent. And here also the probability that you will get a photocurrent output from this region is quite high, lower than that of the space charge region definitely. Space charge region almost close to 100% surety that you will get a photocurrent out of that. In this third region, the probability of getting the photocurrent due to the electron hole pair created, that probability is quite high, though not as high as the space charge region, but still it is okay. So, I mean this region is also okay. So, second region and third region both are sort of okay, we can deal with them. First region, the top region, the dead layer is no go, that is not where we want our photons to get absorbed. And now we go to the fourth region, deep in the solar cell. So, fourth region indicates absorption outside the diffusion length of the electrons. So, here in this figure you have the fourth photon you see here, it is getting absorbed in the bottom of the solar cell below one diffusion length from the space charge region. So, somewhere here deep in the solar cell. This guy also creates one electron hole pair because of our assumption that we are considering those photons which have energy more than the band gap. Now, what happens to this guy? Now, again this electron also does not have a very any particular direct electric field which can attract it or pull it to contribute to the useful photocurrent. This electron also, and again because it is p base, it is not very heavy doping, this also will not recombine instantaneously. But what will happen, again this also sort of wanders aimlessly here and there, but this guy is more than one diffusion length below the space charge region, that is the problem. So, it is not very likely that this electron will land up at the edge of the space charge region and from there it will go to the n plus side and contribute to the useful photocurrent. Most likely is that if we just leave the solar cell like this, it will go on wandering here and there and just get absorbed at some point, it gets absorbed within the p base, basically recombine with some hole. So, there is a particular diffusion length for which it can move around, there is some diffusion time for which time it can remain independent, but after that time it gets recombined. We will look at those carrier lifetime and diffusion length in more detail in the next lecture, but for now qualitatively we will understand that this particular photon number 4 again has a very low probability. So, again here the probability that this electron hole pair will contribute to a photocurrent, that probability is very low, quite less likely, because we are at a much deeper layer of the solar cell, much below the space charge region, more than one diffusion length below the space charge region. So, if it does not contribute to the photocurrent, then what will happen? It will just heat up the solar cell. Same with the dead layer also. You create electron hole pairs and then again they recombine. So, the absorption of the photon, basically your cell is absorbing some energy, but those electron hole pairs, if they are not contributing the photocurrent, they are getting lost in the solar cell itself, recombining back with the electrons and holes, recombining back with each other. Then that is just a sort of heating up of the solar cell, which is not desirable. So, this region also does not produce very productive results with respect to the output of the solar cell. But the good thing is that something can be done about this. While in the dead layer there is not much scope of doing anything, but in the fourth region we can do something to improve this particular behavior of the fourth region. But before we talk about that, what can be done to improve the behavior in the depth of the solar cell, let me ask you a quick question. We talked about so many electron hole pairs being created at different depths of the solar cell, and some of them recombining back within the solar cell, some of them traveling to the external circuit and contributing to the photocurrent or output of the solar cell. So, at this point, before I go to the next topic, I would like to ask you this question. Would the available electrons and holes in the solar cell be used at some stage? Because you are continuously absorbing photons, creating electron hole pairs, splitting them apart, and then you are pulling away the electrons and holes on different sides of the solar cell and then sending them out of the solar cell. So, is it a possibility that at some point, we understand that electrons and holes are in huge number, as we saw in the previous numerical example, maybe of the order of 10 to the power 17, 10 to the power 19, that type of order per centimeter cube. So, it is a large number, but still, because we are continuously creating electron and hole pairs and then sending them out of the solar cell, is it a possibility that at some stage, at some point, all the electron hole pairs present in the solar cell will be used up? What do you think? Think for a moment. Well, if you think about it logically, this is never going to happen. Can you say why? The answer lies in this figure here. So, when you split the electron hole pair and you send them out of the solar cell, it is not like they are just getting lost in the space or somewhere outside. Basically, for any useful work to be done from a solar cell, to get any useful power output from a solar cell, you need a complete electric circuit. So, there is an external circuit, so you have a negative contact of the solar cell, there is a positive contact of the solar cell, and then there is some load here which is shown here by this rectangle. So, there is an external load through which the positive and the negative contacts are connected. So, all these electrons which are going out of the solar cell, they will travel through this conductor, go through this load and come back through the bottom end of the solar cell. So, the electrons will move like that, and as we understand, the flow of current is opposite to the flow of electrons. So, the current goes like that. So, because it is always a closed circuit, whatever electrons are taken out of one side of the solar cell, they go through a external conductor, through a load, and they come back through the bottom of the solar cell. So, this is not going to happen, that at some stage all the electron hole pairs will be used, that is not possible. So, it is sort of a continuous cycle, electrons are getting out from one end of the solar cell and coming back from the other end of the solar cell. So, it is just in circulation like that. Okay, so because that is some confusion many students get when they understand the solar cell. So, having cleared that confusion or scope for doubt, now let us come back to our question we asked a few minutes earlier. We asked the question that what happens, how do we improve the productivity of the fourth region, because this region has a very low probability of contributing to the photocurrent. So, fortunately, a lot of people have worked on this problem and they have come up with a very interesting solution. Let us see what is that solution here. So, the solution lies somewhere in this concept known as the back surface field. Let us see what is this back surface field. It is a very interesting trick actually. So, let me draw a schematic of a solar cell which we just now looked at. So, this is your N plus emitter and this is your P base. There is a space charge region here, something like this, right, and let us say this is, so this is your space charge region, and then this is one diffusion length below, this is Ln here, let us say one diffusion length below the space charge region, and now this is my fourth region where I just now saw that the productivity is not very good for the photocurrent. Now, we can use a very interesting trick here basic concept of electromagnetism to improve this operation of the fourth region. So what we do here is that at the bottom of this fourth region, at the base of the solar cell, we do a very heavy doping of P plus type. So there is, I will add another layer here of P plus. So by now you must be well versed with the terminology we are using. When we are saying N plus means very heavy doping of donor atoms. When we are saying P plus, we mean a very heavy doping of acceptor atoms. So this is very heavy doping of donor atoms on one side, and when we say P plus, this is very heavy doping of acceptor atoms on this side. Whereas the P type is sort of, you can say, medium level doping of acceptor atoms. So now what we have done here is that as we have created a very heavy doping of acceptor atoms at the base of the solar cell, now this is a very interesting phenomena which will happen here. It acts almost like a p-n junction, but not really a p-n junction. So it is like a P and P plus interface. So now what will happen here, as you can probably understand, there are a lot of excess holes here. Okay, so many excess holes. P type also has excess holes, but not in that much a heavy concentration. So just a schematic diagram to represent that. So there are excess holes on the P side, but not a very heavy concentration. P plus also has excess holes, but in a very heavy concentration. So again, as we have been discussing, whenever you put two types of semiconductor materials with differential doping and they are touching each other physically back to back, there is a physical boundary between them, then there is a diffusion of charge carriers from the higher concentration side to the lower concentration side. So here what happens, that many of these excess holes will diffuse to the P type. Now as these excess holes will diffuse to the P type, the same analogy you can understand here is that excess holes, as we understand, are positive charge carriers. So excess positive charge carriers will leave the P plus side. So P plus side becomes relatively negatively charged, whereas your P type becomes relatively positively charged, because P side has got excess holes, excess positive charge carriers. So this behaves like the positive plate of a capacitor, whereas your P plus side behaves like a negative plate of a capacitor. And now you see this thing here, again there is a field known as the back surface field. So we are calling this as the back surface field. In short, BSF. I will come to that acronym in a while. Now back surface field, now what happens, that you have created one field at the bottom of the solar cell also. Now interesting thing is that, now let us say some photon gets absorbed in this fourth region of the solar cell and it creates a split of an electron and a hole. So you have electron here and you have a hole here. Now what will happen, this electron, this will again wander sort of aimlessly here and there, and let us say if it comes near the edge of this back surface field, which is very likely because this is within one diffusion length of the bottom of the solar cell. So it is very likely that it can land up near the edge of the back surface field. As soon as it lands up here or close to this electric field will propel the electron upwards. It will repel, because like charges repel, and as we said just now, P plus is negatively charged. So as soon as your electron comes near the edge of this back surface field, this existing back surface field will propel it up towards the space charge region, and there will be a force, electromagnetic force obviously, because like charges coming closer and the charges will repel. And this electron now which lands up here in the third region, now there is a likelihood that it can go up to the space charge region, and then from there this existing electric field will absorb it and send it to the N plus, and from there to the external circuit. So that is the idea of a back surface field. So with this is a very common practice now with all the practical solar cells which we get, they come with this type of, most of them they come with this back surface field type of arrangement, and that ensures that my fourth region also becomes quite productive. So space charge region is definitely the highest, most productive one. then your third region within one diffusion length also was quite productive, and now your fourth region also becomes quite productive. With the back surface field, you are propelling the electrons up towards the depletion region or space charge region, and from there they can be sucked up by the existing electric field and then go to the external circuit, contribute to the photocurrent. And to help you understand and to retain this particular concept, you can always refer to this acronym BSF. So those of you who are listening to this lecture in India probably are aware of our defense forces which we have in India, and one of the major defense force in India is known as the Border Security Force, BSF. And that, what is their mandate? They have to protect the borders of the country. So they don't allow any trespassers to enter inside the country. They repel them back. If any infiltrator is coming trying to penetrate in the boundary of the country, they repel them away. So similar thing is happening here. Your back surface field, if your electron is sort of wandering here aimlessly and coming near the border of the P and P plus region, this BSF will push it away and propel it towards the back to where it belongs, towards the space charge region and towards the N plus emitter. So that's the back surface field or BSF in action in the solar cell. So that is it for today's lecture. We have looked at the detailed working of a solar cell and the different phenomena which are happening in the solar cell at different depths of the solar cell. In the next lecture, we will look at some other interesting phenomena of solar cell known as the recombination phenomena in the solar cell. So hope to see you in the next lecture. Thank you.